All right, the recording is on. And so good morning, good afternoon, or good evening, everyone, depending on your time zone. And if you'd like our speaker today, you should select all that apply. My name is Chris Kapolki, and I'm today's host. And we'll begin with a couple of reminders. So first of all, we have a website, which you should visit, absolutely visit every day. You can see the upcoming talks there, as well as slides and videos from past talks. We also have a mailing list and a Google Calendar, and if you want to find out more about them, you should visit the website. That's where those things are. As always, we are recording the talk, and so if you become a part of the recording, you'll be part of maybe online posting if Dmitris agrees after the talk. But nonetheless, please don't be shy. Please ask questions. And so I think that's it for the announcements. And so it's a pleasure to introduce an old friend, Dmitris Tsementzis. Like, we've known each other for a long time. He's not old, not at all. So Dmitris Tsementzis, who will speak today on the first order logic with isomorphism.
Okay, thank you. Thank you for having me. As usual, I cannot see myself, so if anything is happening or if I kind of veer off the screen, please, someone do let me know. Okay, so I'm going to talk to you about first order logic with isomorphism. And let me begin by the obvious question. What kind of thing is this first order logic with isomorphism that is in my title? So let me begin by an even more interesting question or basic question. What is a foundation for mathematics? Okay, so one basic picture that one can have of what a foundation for mathematics is that it consists of three components. You have a formal theory of some kind, and you take that formal theory to be axiomatizing some kind of universe of objects, and you take that universe of objects to be such that all of mathematics, all of real mathematics can be formalized in terms of it. The fact that this can happen is why such a setup would be called a foundation for mathematics. Okay, so what are usually referred to as set-theoretic foundations, one setup for set-theoretic foundations would have the ZFC, Zermelo-Fraenkel set theory with choice, say as its formal theory. There are many variants, of course. We take this ZFC to be axiomatizing, to be describing the universe of sets, the so-called cumulative hierarchy of sets. And we, the idea that all of mathematics can be formalized in terms of V is kind of well established. You just take any mathematical object like the number one and you formalize it, say, as the singleton set. In terms, again, of this way of breaking it down, the Univalent Foundation, so I'm sort of going to define what I mean by the Univalent Foundations, is a system in which the formal theory is some kind of homotopy type theory, many variants of which exist, which we take to be axiomatizing the universe of homotopy types, or potentially a nested sequence of universes of homotopy types. And the fact that all of mathematics can be formalized in terms of homotopy types is kind of the very new idea. This idea that mathematical objects can be stratified, can be organized according to their H level. And indicatively, you know, instead of sending one to the singleton, we say would send one to the homotopy type of a disk, say, to a contractible space. Okay, now, let's say that this is kind of a basic visual of what a foundation of mathematics is. Now, whenever you have such a picture, you also might consider something like a basic logic for such a foundation. So this basic logic would again be a formal system that has some kind of semantics into the universe of objects and can also be formally interpreted into the formal theory. So for example, in set-theoretic foundations, you have first order logic with equality, which of course can be interpreted into ZFC. In fact, it's strictly speaking a subset of ZFC, and has famously sound and complete semantics in V, in terms of which we can do things like model theory and talk about models of groups and monoids and all that kind of thing, all that kind of stuff. So some kind of analogous thing should be replicable in the context of the univalent foundations. I mean, it already exists if you take somehow fragments of Mardlev type theory to some degree. So first order logic with isomorphism, what I'm calling first order logic with isomorphism, by analogy to first order logic with equality, is a basic logic for the univalent foundations in this sense. Namely, it can be interpreted into homotopy type theory, but is maybe a subset thereof, and has sound and complete semantics in homotopy types. And roughly what the system is first order logic together with a notion of dependent sorts, together with a notion of path structure. And first order logic together with dependent sorts was a system that Makkai called folds and began studying in around 1995. Invented in around 1995. And much of what I speak there will build on his work. Okay, so let me tell you in a nutshell what this is and kind of give you the plan for what I'm going to talk about. So the syntax of first order logic with isomorphism, which I might abbreviate FOLiso so that I don't repeat the phrase a million times. The syntax consists of signatures, which are inverse categories with certain specified objects. And the language is extracted as it is extracted in folds. Now, I want to make a terminological distinction here, since I know there's obviously, if not the majority of the audience is going to be type theorists. By signature here, the distinction between signature and language follows the distinction that one usually makes in mathematical logic. So signature here, I mean a similarity type, namely a collection of function relations and constant symbols. So for example, the signature for groups would consist of one sort, an operation, and a constant symbol. The language, on the other hand, is the notion of well-formed formulas over a signature that has been fixed. So a sentence like this would be a sentence over the signature for groups. So this is just a terminological clarification. There's a distinction between signatures which are defined first, and then the language we extract out of these signatures, which is something that doesn't really happen in type theory. Okay. Semantics are going to be reedy fibrant diagrams over these inverse categories with a specified interpretation for the specified objects. And the proof system, the deductive system, is going to be essentially sequent calculus for first order logic together with some rules governing these new specified objects. So this combination of syntax, semantics, and proof system is what I would maybe traditionally understand as a logic. And so I'm going to begin by giving you all these three components, describing all these three components. And then I'm going to talk about soundness and completeness, theorems, and finish with some applications. Okay, so let's begin. So the syntax. So let me call a signature, let a signature for the time being, these are not going to be the FOLiso signatures, there's going to be a notion of signature, be an inverse category L with finite fan out. An inverse category intuitively is a category in which all arrows point in one direction. And there's no infinite descending chain of arrows. A condition which you may encode, for example, by saying that there exists a functor from L into the partially ordered set of natural numbers that reflects identities. Namely, if an arrow becomes an identity under this functor, then it was an identity to begin with. But intuitively, we can just think of it as a category in which all arrows go in one direction. And finite fan out means that for any object in this category, the slice on that object, namely the set, say the category or the set of arrows coming out of it is finite. Hence the term finite fan out. So just to give a few trivial examples or easy examples, the one object, one morphism category is a signature. This category with two objects and two arrows between them is a signature. This category with the following relation is a signature, and it's going to act as a running example. So I'm going to give it a name. I'm going to call it LRG, RG for reflexive graphs, because this will be can be understood as a signature useful for formalizing reflexive graphs. And the semi-simplicial category, so essentially a skeleton for the category of finite sets and injective, the opposite of a skeleton of the category of finite sets and injective functions is also a signature in this sense, because even though it's infinite, it has finite fanout, because at each level, there's finitely many arrows coming out of it. Okay, now I'm going to describe a construction in terms of which I'll describe the kind of the fundamental constructions in the syntax. It's quite a simple construction. Let L be a signature in the sense I just described, and let gamma be a finite set-valued functor, where finite here means that the union of its values is a finite set. So in particular, if there's infinitely many objects, only finitely many, the functor is non-empty at only finitely many values. So out of this data, we define a new signature, which can be called, and I'll be calling the extension or the collage of L by gamma. So you're gluing somehow gamma into L, which is basically the category whose objects are the objects of L plus a single new object, such that the boundary of that object is equal to gamma, where the boundary here means the reduced covariant Yoneda functor on that new object should be equal to gamma, and where the reduced covariant Yoneda functor is the Yoneda functor, except at the object, its value at the object itself is empty rather than the singleton, which it would be, because in an inverse category, there's only one arrow from an object to itself. You can just think of it as a boundary. Okay, just to give you an example, to give you a feeling of what this construction does, let L be this category with two arrows, D and C, from A to O, and we're going to glue to it the context I and X. So this is the set-valued functor that takes A to the singleton I and O to the singleton X. So what does this become? Okay, well, you have the category, you add an object to it, represented by the green asterisk. Arrows from the asterisk to A are the elements of gamma at A, which is just I, and similarly for X. And then the composite of the new arrows with the old arrows is determined by the action of the functor on the new things. The action of both arrows on I goes to X. So in fact, we see that D composed with I is equal to C composed with I. And therefore, this category is isomorphic to LRG, the category we started with. The category I said is going to be a running example. Okay. All right. Now, these are the sort of the key constructions in the syntax. Let L be a signature. Let K be an object in the signature. I'm going to refer to these objects as sorts sometimes. When I say sort, when I say object, I'm going to essentially use them interchangeably. This object might have multiple arrows coming out of it. Okay, so now I'm going to define some new signatures based on top of this starting signature L. So the first one is this one, GKL, which is L collaged with this context, extended by this context, where this is Y is the Yoneda functor and partial is the reduced Yoneda functor. So it's just gluing two boundaries, essentially, gluing YK along their boundaries, their common boundary. And concretely, what it means is you add one new object, two arrows from the new object into K, such that G following S is equal to G following T. All right, that's what it means. I'm going to describe the intuition in a bit. The second construction I'm going to call RKL. And again, it's a collage of GKL. You collage another context onto GKL. And I'm not going to describe the context. I'm going to tell you concretely what it does. It adds to, it outputs a signature which adds, again, a single object and an arrow row into this object that we added in GKL, which I'm going to call the isomorphism sort of K. And the relation S rho is equal to tau rho. Okay. And finally, suppose we also have an arrow F from A to K in L, then we can define a new signature TFL, which is RKL extended by a, again, far more complicated context, which is easier to describe concretely. So what this TFL down left, the blue new category, is a signature in which we've added an object, 2 arrows into A and 1 arrow into the isomorphism sort at K, where K is the codomain of F, such that the following relations hold. FF1 is equal to SEF, FF2 is equal to TEF. For every arrow Q coming out of A, it co-equalizes F1 and F2. And for every arrow G coming out of K, it co-equalizes FF1 and FF2. Okay, this is a bunch of symbols and equations. Let me give you an intuition about what these are supposed to mean. So we're adding things to the syntax, recall. So the isomorphism sorts, as the notation suggests, are to be thought of as isomorphism sorts on K. If you think of K as a type of some kind, it's going to be essentially the identity type. So you can think of the isomorphism sort K as a family over 2 copies of K, a type family over 2 copies of K. That's what the arrows S and T represent. That takes, say, any 2 terms of those types and sends them to their identity type. Okay. The RKs are to be thought of as reflexivity predicates on the isomorphism sort. And the idea there is that they pick out the reflexivity, the trivial isomorphisms or paths or whatever you want to call the terms of an isomorphism sort. So you can think of them as a type family over this sigma type there that takes a term of type K and a loop on that term to the identity type Q to reflexivity at X. So it's reflexivity up to an identity. And TF is to be thought of as transport in position F of A. Now, how to exactly to regard F as a position shouldn't really be clear at this point, or how to regard A as a type family dependent, say, only on one thing. But roughly to give you an idea, which the semantics will make clearer later, if you think of tau F as a 3-place relation, then it relates EF, F1, and F2. If and only if F2 is the transport of F1 along EF, where EF, since it's landing into the isomorphism sort, is a path. Okay, and F1 and F2 are 2 things in 2 fibers. F1 is in the fiber over FF1, F2 is in the fiber over FF2, and EF is a path from FF1 to FF2, and the relations that we saw earlier ensure that all this kind of thing makes sense. Okay.
Can I ask a question?
Sure, yeah.
Can you go back to the previous slide?
Yeah.
So I think you said that any arrow Q from A will equalize F1 and F2.
Sure, yeah.
So wouldn't that mean that F equalizes F1 and F2?
No, sorry, any arrow except F.
Oh.
That's what ensures that that A is a type family which can only vary at F. So the rest of the context is somehow kept constant. But the only variation can be at position F. Yeah, sorry. If I said every arrow out of A, I meant every arrow except F.
Okay.
Okay, so now we can define the class sigma iso of signatures for first-order logical with isomorphism, the system that I'm calling first-order logical with isomorphism, to be given as essentially the closure of signatures under these operations. So every signature in the sense of an inverse category with finite fan-out is a signature for first-order logical with isomorphism. And if something is a signature for first order logic with isomorphism, then GKL, RKL, TFL, and L collaged with some gamma are also signatures for all applicable F, K, and gamma. And F, for example, may include the S and T's, the arrows that we add when we add something like GKL. So to give you a feeling for what kind of things these signatures are, suppose we start with this signature, which, although I don't expect this to be clear, and I'm going to give the example in more detail later, to anyone who hasn't seen this before, this is a signature helpful for actually formalizing the theory of categories, the first order theory of categories. So if we start with this as a signature, then hit it with RO, we add the ability to talk about isomorphisms in O together with picking out trivial isomorphisms. We can hit it with G iso O, and this allows us to talk about isomorphisms between isomorphisms in O, or equalities between equalities in O, if you want to think of isomorphisms as equalities. And similarly for A, and we can also extend this thing, we've added specified stores, we can also extend it by some new thing, say U, which would allow us, as we will see in an example later, to relate, say, terms of type A to paths of type iso O in the isomorphism sort. Okay, so this would be for an example of a signature in first order logic with isomorphism, and it's an important example because over the signature we can in fact formalize the theory of univalent categories in the sense of the HoTT book. So one can think of, if one thinks of folds as a system in which you can formalize any first order theory invariantly, first order logic with isomorphism allows you to formalize any theory which might include axioms that involve paths. That's the basic idea. Okay. Now, let L be a signature of first order logic with isomorphism. I'm just going to say signature now, and it'll mean, in anything that I say, it'll mean signature in first order logic with isomorphism. The syntax of L is extracted as was done by Makkai. We have contexts of variables in L, and these are just going to be finite set-valued functors. We have formulas for any such L, which are defined inductively as follows. True and false are always formulas. Phi and psi are formulas if phi, sorry, let me be clear here. Formulas in a context gamma, right? In a context of variables gamma. Formulas whose free variables are among those in gamma. Phi and psi are formulas if phi, comma psi are formulas, and the same with other connectives that we may wish to add, like or and implies. And if phi is a formula in this extended context, which, since I'm introducing the syntax functorially, this would be just the push out along the boundary inclusion of whatever the dependencies of X are in this context. So the arrow from partial K to gamma down below. I hope this is not the point at which the not having a mouse is making it difficult for me to express where I'm pointing, but I'm pointing at the bottommost row of what is on the screen right now. If it is unclear what I'm referring to when I'm describing it verbally, please someone stop me and ask me. So what this map is determined by somehow what X depends on in this context. Okay, so this is just this push out. So whenever we have a formula in this extended context, then we can bind X, and we get the formula. There exists an X in K such that F, such that phi, and similarly for the universal quantifier. Okay, so these are the formulas. And then we can define sequence, which, as one does, usually in first order logic, as just a syntactic symbol. Gamma, vertical line, phi implies psi. The first vertical line here is not the same as the second vertical line. The first vertical line is part of the sequence. The second one is just the set. it's a sequent if phi and psi are formulas in context gamma. And the sequent should be read as one reads a judgment in type theory. In context gamma, phi implies psi. And substitutions are natural transformations between contexts with the obvious action on formulas, which, as with everything with substitution, is never really obvious, but requires a bit of care, but is kind of technical, and I'm not going to go into it too much there. Yes?
I was going to ask another question.
Yeah.
In your definition of the formulas, I don't see how you get anything interesting. How do you bootstrap your formulas and get some non-trivial formulas?
So I'm going to give an example which hopefully clarifies that. But let me say now, yes, the idea is everything, the only way to express things that are interesting is by saying there exists something is true. So the only things that you express are the inhabitation of sorts, essentially.
Okay.
So really, the way you build things up is you start with true, and then you say there exists something that is of sort, say K, true. Would be like saying sigma of some type 1. I'm gonna give an example now that will hopefully clarify this point. But yeah, thank you. Okay, yeah. So let's give an example to see how this language works. Let's go back to this example of LCAT. Here is an example of a context. So it sends I to sigma, A to F, and O to X, and the action is shown above. So this is a context in LCAT. And if you don't want to think functorially, what this context expresses is what in type theory you would write in this way. X is a term of type O, a variable of type O. This is a context. F is a variable of type AXX, where A is a type family appropriately dependent on O, and similarly with sigma. Okay. Now to answer, Dan, was that you who asked the question? Because I can't see.
Yes, it was me.
Okay, all right, okay. Now to sort of get back to Dan's question, what would be the formulas, for example, in this context? Well, without having done anything, the only really interesting formula to have to begin with, other than false, is true. Okay, but once you have true, you can begin binding, right? So I can bind sigma and get a formula that says there exists a sigma in I, true. I can then bind F to get there exists an F, AXX, there exists a sigma, so on and so forth. And say I can bind the last variable to actually get something in the empty context, so a sentence. For all X in O, there exists an F from X to X, such that there exists a witness to the fact that X is that F is an identity, if you read the identity this way. So this would be a formula that expresses something non-trivial, like there exist identity arrows for every object. Okay, and analogously with more complicated contexts using T, this would be a context that basically allows you to express commutative triangles, sigma being a witness to the commutativity of this triangle. You can write down sentences that say, for instance, that for any 3 objects and for any 2 composable arrows, there is a third arrow such that the triangle commutes. So there always exists composites. So that's kind of how you do logic in this framework. And similarly, you can express all the axioms for categories. You actually need an equality predicate on A, but I'm sweeping that under the rug for the time being. Okay, and the addition that first order logic with isomorphism gives you is that, okay, over LCAT you can axiomatize categories, but over something like LUCAT you can axiomatize univalent categories, namely by adding these logical sorts, isomorphism sorts, and then using these, something like U in purple up above, to express an axiom, say, of this kind. that UFP, again thought of as a binary relation between terms of type A and terms of type iso O, is a bijection between isomorphisms in the sense of terms of the isomorphism sort and category isomorphisms, i.e. isomorphisms in the sense of the LCAT structure. And you do so by, again, expressing it in terms of these sentences, and you can write down the axioms and actually get univalent categories. Okay, I say get it, but of course I haven't talked about semantics at all. This is all syntax still. So I'm saying isomorphism sorts and reflexivity and transports and all that stuff. But again, this is just purely syntax at this point. So let me tell you what the semantics are. Hopefully the syntax has given you an idea of what the semantics should be. So once again, let L be a signature. I need to tell you what an L structure is, okay? An L structure is a functor from L to S, where S is, say, a homotopy category of spaces, for example, simplicial sets, or anything that you like that it will include the notions that I will explain below. So I'm going to keep it vague for now what it is exactly. And M is a redefibrant functor. And the fact that I'm talking about redefibrant tells you obviously that S needs to have some notion of fibration that behaves in the way we expect it to behave. Okay, so what this means is, is a redefibrant functor together with some specified actions on the specified sorts, the isomorphism sorts, the reflexivity predicates, and the transport structure. Okay, so the functor takes any sort in L and gives you a space, and the redefibrancy condition means that the canonical map from that space to the limit of all the things that are below it somehow is a fibration. It's kind of a technical condition. The fact that M, bottom right of the screen, the fact that M is included in this condition obviously indicates that what it means for M to be redefibrant needs to somehow be defined inductively, but this is kind of a well-understood, well-known theory about redefibrant diagrams. Okay, and now what we do is, so it's a redefibrant diagram such that isomorphism sorts get sent to path spaces over MK, with the two arrows being the source and the target of the paths. Okay. Reflexivity sorts get sent to something that I'm now going to denote as a sigma type. And formally later, we're going to see that actually this is another way of giving the semantics directly into type theory. Because at this point, I feel it becomes easier to write a homotopy type in terms of the sigma type. Sends it to the type of points in MK, loops X in MK, a point in MK, a loop on X, and a path from the loop to reflexivity on X. Okay, with the action being sending the thing to Q. Okay. And once again, suppose we have an arrow from A to K, F, and we have, so then we get fibration MF from MA to MK. Then this is going to get a little hairy now, but I'm going to spend the next slide kind of hopefully making that a bit clearer. The transport sort gets sent to a relational form of transport, essentially. So TF, the interpretation of tau F, is the space whose points are a choice of 2 points in MK. So now I'm looking at what's below the sigma type. I can't point to it, but I'm pointing at my finger. 2 points X, Y, and MK, a path from X to Y, a point A in the fiber above X, a point B in the fiber above Y, and a path from the transport of A to B. Okay. So let me, this is kind of the key construction and really what allows one to prove the theorem. So let me spend one more slide illustrating this. So for some arbitrary signature in first logic with isomorphism, we have this setup, say, the setup that we've already seen. And the interpretation of the setup is, okay, the arrow F gets sent to a fibration. And now suppose you have two objects, X and Y, sorry, 2 points, X and Y in MO. These are the fibers in MA of these 2 points. And these are 2 points in the fibers, on the fibers. And these 2 points are what the meaning of the 2 arrows from tau F to A are. It's picking 2 points on 2 fibers. And now suppose we have a path from X to Y, okay? So we have that gives also the meaning of the arrow from tau F to the isosort of O. Then we get a point here, P, say, pushing it forward, the push forward of A. And then we have 2 points over the same fiber, and we can talk about paths between them. And then the interpretation of this tau F thingy is the space of all those paths with kind of the clear action of the maps. Okay, so that's it. And again, the intuition here, we're making things difficult for ourselves because I want to express everything relationally. Everything is relationally. So there's no operations, there's no terms, there's no constant symbols. Not because obviously it's easy to think about it in those terms, but because it's easier to prove general theorems about things you can formalize in this manner. Okay, so this is always a design choice in the system. I don't expect, or I think it is reasonable to expect anyone to think of transport in those terms, but it is an equivalent way of thinking about it that makes it easier to prove things. Okay. Finally, I need to tell you what the interpretation of the syntax is. So this, I've told you what an L structure is for any given signature L. And so take any L structure M now, read the different diagram with this specified action on the specified sorts. And let's call any functor for any context gamma, any natural transformation into M, we can call, or we can think of as a realization of this context in this L structure, right? And just write the set of all these things as M gamma. And again, I'm using notation that I think Makkai also used. So then the interpretation of a formula in a given context, rather the extension of a formula in a given context is given as follows. The extension of the formula true in any context is the set of all realization. It's the top element. The extension of the false formula in any given context is the empty set. And again, I'm saying empty set, but that's because I'm kind of working in a vague set-theoretic meta-theory. If you want to work in, you can probably say most of these things in type theory too, so you can take this to be the empty type. The extension of the logical conjuncts is kind of the Boolean translation, straightforward. The interpretation of the quantifiers is a bit less straightforward, so let me outline this in slightly more detail. So the extension of the formula, there exists an X in K such that phi in context gamma. So this intuitively would be the set of all those realizations of gamma in M that satisfy this formula, okay? And that's what the definition expresses. It's those alphas in M square brackets gamma, those realizations alpha, such that there exists the first A up there is after the vertical line is not alpha, it's A, in MK, in the interpretation of K, such that the boundary of this A is equal to the boundary of this alpha. So this A could act as a thing in MK that has the boundary determined by alpha. And the appearance of the existential quantifier in both the left-hand side and the right-hand side kind of tells you what
does it mean
this is.
to have an A and MK? If we're in this.
Well, it's a point of the space, say.
Oh, okay.
It's a point of the space, yeah. Again, I'm saying I'm working in kind of a vague set theoretic meta theory here. There's no, there will be some technical obstacles. I don't think there's a principled obstacle why you wouldn't be able to express all these things internally in some type theory too. So you can also read this as there exists a point in the space MK such that the boundary of this point, because this is kind of somehow fibered over many things, is the same, literally the same as the boundary determined by alpha. Okay, the same for the universal quantifier. And once again, there's obviously things you need to prove with respect to substitutions that are obvious, but are not really obvious, and they require a bit of care, but are technical and do not belong, at least in this talk. Okay. All right, and given this notion of the extension of formulas in a given L structure, we can get a notion of satisfaction. So we can say that a given L structure satisfies a given sequent gamma phi implies psi, if and only if the extension of phi in gamma at M is a subset of the extension of psi in gamma at M. So it's exactly the kind of the notion that you use in first order logic. And in terms of this notion of satisfaction, you can define the things that you define in traditional mathematical logic, like an L theory would be a set of these L sequence. For example, the FOLiso theory of univalent categories would be the theory which includes all the sequence that express the axioms of categories together with the fact that there's a definable bijective relation between isomorphisms in the sense of categories and isomorphisms in the sense of isomorphism sorts. A model of an L theory is an L structure that satisfies all the sequence in the theory, and so on and so forth. You can play around with kind of translating traditional notions and playing around maybe with defining some new notions, like maybe another definition of an N theory as an L theory for some first order logic with isomorphism signature L, where L is of height N. Okay, you can do all these things, but let me kind of illustrate what this notion of satisfaction means now with an important example. Okay, let's go back to again to this situation where we have this diamond of a fibration, isomorphisms, reflexivities, and transports. Okay, now given the semantics that I've given you, for any point X in MO, you know, as the question, was that David who asked me the previous question? Anyway, I think I'm going to call the person who asked me the previous question David. I think it was David, but to answer David's question, so X is in MO, so it's a point of a space. So it's being a point of a space, it has a trivial path to itself. Okay. And since it has a trivial path to itself, given the semantics, this trivial path also is an inhabitant of the interpretation of the isomorphism sort. And there's a proof, top right corner represented by a dot, that this path is actually the trivial path. And this is an inhabitant of the reflexivity sort RMO. And so in any model, in any L structure, in the sense that I've outlined, this sentence will be true. So it will be true in all models, that for any X, there will be a Q, a loop that is trivial. So this is like the id intro rule. So this will be true in all models. And similarly, if you take the fiber over X and you take a point in the fiber and you transport it along the trivial path, you transport it to itself, which means that every model will satisfy a sequent. I used the first one I wrote as just a sentence, the second one as a sequent, just to kind of also indicate that if you're working with full first order logic, the distinction between sequence and sentences doesn't really matter. But working with sequence, I think, provides some extra generality at no real cost. So I'm writing the second one as a sequent. So in any context which includes an object, a term of type O, a loop from X to itself, a term A over the fiber of X. If the loop is trivial, then A will be the transport of itself along Q. That's really how to read this. Okay, so in the semantics that I've given you, we get that these things are valid, they're true in all models. So if we want to come up with a notion of provability that captures all valid sentences, then these two things will have to be considered, and this is what motivates the definition of the proof system, the final component of first-order logic with isomorphism, which I'm going to denote by this curly D iso. And this curly D iso, the proof system, is essentially just a sequent calculus for first-order logic, including all the usual rules like conjunction, introduction, and so on and so forth, together with the two axioms that I just spoke about, namely the analog of the id intro rule, there is always a trivial path, and the analog of the fact that transport along reflexivity is identity. And crucially, of course, an analog of the id elimination rule, of the J rule, which expresses, in a slightly peculiar form, expresses the thing that I expect most of the audience is familiar with, namely that if you can prove a statement for a loop that for reflexivity, for a single X and reflexivity, then you can prove it for an arbitrary path. Okay, I'm not going to dwell on the notation because it is pretty much the same thing, except expressed again relationally without terms. So instead of having a term reflexivity, we have a proof that some loop is reflexivity. Okay. All right. So now we have the proof system, the syntax, and the semantics. So we can meaningfully state a soundness and completeness theorem. And since maybe the audience is mixed between type theorists, computer scientists, homotopy theorists, it's kind of what's brilliant about this field. Let me just, for the sake also maybe of taking a breath, state what a soundness and completeness result means. So soundness and completeness result is a result where you have a notion of provability, of deduction, and you want to prove that it's equivalent to a notion of validity, namely truth in all models of some kind. So in our setting, so the left to right direction is soundness, the right to left direction is completeness, right? Okay. So provability for us in this context in first order logic with isomorphism, for a sequent in first order logic with isomorphism, will be derivability in this system D iso that I just sketched for you. Validity will be that for any L structure, M satisfies the sequence. So true in all models, so to speak. But I'm actually not going to use this notion. I'm going to use a notion that will be equivalent to it modulo initiality. And I have practical reasons not to use that notion that will become maybe clearer later. And I can maybe go into what the issue is, but I won't for now. I'm going to replace this notion by something equivalent, namely a direct interpretation of first order logic with isomorphism into homotopy type theory. So rather than a semantics in the traditional sense, I'm going to work with a direct interpretation, namely a process through which any sequent in first order logic with isomorphism is translated into a judgment in type theory, and in particular in homotopy type theory. And so the notion, the theorem of soundness and completeness theorem is going to equate these two things, derivability in D iso with derivability in homotopy type theory of certain sequence. Okay. Let me quickly now describe to you what this I is. Okay, I've been talking about reedy fiber and diagrams and all these things, but really to a type theorist, and it is actually also the perspective that is more natural to me, these things are just sigma types, and the gammas are just contexts, and the form. Yeah.
Yeah, I'm sorry, I didn't want to interrupt you, but I was just wondering, your first order logic, does it include, I mean, is this classical first order logic?
It doesn't matter. You can add it or you don't. I'm not assuming that LEM is part of the DISO system.
But because your completeness result refers to HOT, which doesn't usually have excluded middle. So I'm just trying to understand.
Right. Yeah. So it would extend to HOT. So if you were to add the LEM on the syntactic side, and also on the HOT side, then you would also get completeness. But you can also get it without for the coherent fragment first order logic.
Okay, so we could have intuitionistic first order logic, and then really have HOT as it is usually formulated. Okay.
Right. Yes. Yeah.
Okay.
Okay. So the interpretation of FOLiso, and remember, let me pause here. I began with saying that a basic logic should essentially be a subset of the formal systems in a foundation that are strong enough to axiomatize the universe of basic objects that we're talking about. And this kind of interpretation makes that fully precise. The extra thing that happens in this first order logic with isomorphism is that as a piece of syntax, it also has a nice mathematical theory, namely the mathematics of inverse categories with extra structure. Okay. All right. So any FOLiso signature gets sent to a context of types and in some universe, and types landing in that universe, best illustrated by an example. So for example, LRG, the running example, will get sent to the following context. You have a type O in context U, a type A, a type family dependent over two copies of O, and the family I dependent on a sigma type, on pairs of a term of type O and a term of type AXX. Okay. A context, in the sense of a finite set valued functor, gets sent to a context in the usual sense in type theory. So for example, this context that we saw before, expressed as a functor, would get sent to the context. Sorry, when I say this, I mean the thing on the left-hand side would get sent to the thing on the right-hand side, which of course would be a well-formed context if we already have declarations of O in U and A, O times O into U on the left, which we have because a context can only be defined once we've fixed the signature. And the formulas get translated in the usual propositions as types translation, modified for HOT, in the sense that the sigmas are truncated. So a formula of this kind is essentially just a notational re-expression where you replace for all by pi's, and I haven't even bothered to replace the exists by sigma because it's really the truncated exists. Okay. And I should say, going back to Dan's question, on the left-hand side, this IFX thing is syntactic sugar for there exists a sigma in IFX dot true. Okay, but we can sort of write it as we do in type theory. Okay, and given these three elements, then we can translate any sequent in first order logic with isomorphism into a typing judgment in type theory. Okay, so this is a typing judgment. Okay, all right. In the sense that so the phi implies psi there gets translated into the interpretation of phi implies the interpretation of psi, where implies is just the non-dependent function type. Okay. All right. So, and in those terms, we can prove soundness and completeness, which, to remind you, because I've kind of set it up rather differently now, means that if a sequent is derivable in first order logic with isomorphism, if and only if its interpretation is derivable in HOT, where being derivable here means that the typing judgment, which is this thing, is inhabited. Okay, it's a statement about inhabitation. So it's a statement about the type theory, right? Not in the type theory. Okay, now the proof of soundness is straightforward. So I'll sketch a little bit how the proof goes. The proof of soundness is straightforward. You basically translate the rules and you see that the interpretation of the rules, say the id elimination rule on the left-hand side, is just a relational version of the usual thing that goes on in type theory. So here you see, instead of having in the context, instead of having just xk in the context, we have a loop and a proof that it's reflexivity, from which we can get this, the thing below it, and then we apply the J rule again, we get phi, and then that gives us what we want. It's a basic induction by the complexity, on the complexity of the rules of the ISO. Okay, so I'm not going to dwell on this too much. Completeness, on the other hand, is, to my mind, extremely difficult. Somehow it's, I was confident that it would hold for many years. It's actually only the last couple of weeks that I've become okay to kind of maybe talk about it publicly more. It seems like a very difficult argument, and for good reasons that I'm going to mention. So roughly the argument is something as follows. Okay, with a few reductions, we can assume that we have this judgment, this term pi, for some phi and some gamma, which I'm dropping the i's there for readability, which are the interpretations of things in FOLiso. And then what the sort of the key steps, which is kind of this very long inductive argument, one then needs to show that in order to derive this term pi, firstly, univalence is inessential. So if it has been used in the derivation, then it is not used essentially. And certain reduction rules are inessential in the sense that we can assume that pi has a certain length, namely the length dictated by the complexity of phi. But all this has to be done mutually with gammas and L's, so it's kind of a very, very long, to my mind, at least for me, very complicated inductive argument. But once these two steps, which are the key steps, are done, then essentially you can proceed by induction on the length of pi and obtain a d iso derivation. And that's the proof of completeness. So it's just kind of a completely proof-theoretic proof of completeness. I'm not sure one would maybe really call it completeness in the sense that the semantics here is an actual interpretation, but it has that kind of feel for me. And again, as I said, modulo initiality, it will be equivalent to a more traditional completeness result. But let me make a few remarks about this theorem. So the meaning of this completeness theorem, and I think the reason why it's difficult, is that it means that any property that is valid for any UF style structure, so any structure that you define like univalent categories or higher categories that involves axioms on paths and possibly on transports and reflexivities and all that kind of stuff, the kind of stuff that is ensured by working in a homotopy type theory, can be derived using only the rules of d-iso. Now so univalence wouldn't figure essentially in any of those arguments. Now this maybe sounds surprising, but it shouldn't be unsurprising. I think the classical analog of this is that the completeness theorem for first order logic with equality in the classical setting of set theory essentially shows you that, for example, anything that is true of every model of the theory of groups is provable without using the axiom of extensionality, because you can just prove it by using the rules of first order logic. So something similar is going on there. If something is, say, true of all univalent categories, then you can prove that thing without using univalence, essentially. Okay. I don't know if this is surprising or unsurprising, but maybe that's kind of the way I explain it to myself. Okay. And so in particular, this theorem establishes a precise sense in which univalence is eliminable if one argues invariantly, namely using this kind of folds-like structure, but where invariantly here means not necessarily not allowing oneself to say anything about strict equality, but also not allowing oneself having some equalities and then arguing invariantly with respect to these equalities and so on and so forth. Okay, so some kind of vague remarks that may or may not be helpful. Okay, so let me conclude with some applications quite quickly. I am, by my count, at an hour. Okay, 12:31 on my computer too. Okay, so I'm gonna take another 5 minutes or so. Okay, so one, and when I say applications, I mean maybe directions of ongoing work. So we know, or it's conjectured, that homotopy theory can't eat itself, but it can digest first-order logic with isomorphism in some sense. So one direction of work would be to have a homotopy type theory in which this interpretation function that I kind of outlined would be in the type theory, would be usable in the type theory. And using a theorem that, or a construction rather, that was proved jointly with Matthew Weaver, we are working on this proposal for a system that we've tentatively called HOT plus I. So HOT plus essentially this interpretation function, which is basically homotopy type theory together with a postulated way to eliminate into the universe from a type of signatures, where signatures here means finite inverse categories, where these are defined as a quotient inductive type in the sense of Altenkirch and et al. And where the interpretation function essentially does what I said it does. It takes a finite inverse category to the appropriate sigma type. Okay. And the categorical semantics for this type of thing, I'm going to mention this because some recent work showed me that maybe it's not too crazy to think about the categorical semantics of this kind of thing. Would be one in which signatures are interpreted as ordered finite inverse categories. The real category of ordered finite inverse categories, where ordering is some technical thing that you need to make sure is there. U would be the category of all contextual categories. And if you pick one such contextual category or C system or whatever model of type theory you're working with, which is, this can be thought of as the interpretation of a smaller universe in terms of which the sigma types that are the interpretations of the inverse categories are defined. Then you have this functor that sends an inverse category to the Reedy fiber diagrams over it. And by a recent, and so this would be the interpretation of the interpretation function. And the fact that this Reedy fiber diagrams over this contextual category actually is itself a contextual category can now be is kind of citable as due to the recently published preprint of Kapulkin and Lumsdaine, and the fact that the category of all these contextual categories is itself kind of a universe, could be the interpretation of a universe of homotopy types, is due to another preprint by Kapulkin and Lumsdaine, the homotopy theory of type theories. So the semantics of this HOT plus I that I'm suggesting would be something along those lines, and it would give a kind of a fully internalized way of doing, in the beginning, some fragment of first logic with isomorphism, eventually all of it. Okay, so there's a few other things that I have mainly as potential questions, but let me jump to the conclusion, and I might mention them if there are questions or if there are none. So the big picture of the thing that I spoke to you about is as follows. For me, the system gives you one way of doing metamathematics in the Univalent Foundations, namely the mathematical study of mathematical theories as they are formalized in the Univalent Foundations, which is very different than how they are formalized in set theory. So it is a kind of model theory. And essentially what this shows is that the metamathematics in the context of Univalent Foundations is equivalent to, in some sense, to the mathematics of inverse categories. And I think that's, for me, is a very helpful and potentially fruitful analogy to keep in mind. And finally, again, going back to this interplay between set-theoretic and Univalent Foundations, if you think of them as two axes, where the v-axis is the axis of set theory and the h-axis, the h-level axis, is the axis of UF, and you have first-order logic with equality kind of interpreting into V, first-order logic with isomorphism, one way in which we want to interpret into H, not necessarily a unique way, one way in which I've proposed. There's, all sorts of questions about how these things are related. There are interpretations of one into the other, but there should be interesting proof-theoretic things to explore here. In a kind of a much bigger, much vaguer and bigger setting, the way in which the cumulative hierarchy of sets exhibits structure once it is mapped by first order theories has been very well explored. And one thing that has come out of it is the stability theory of Shelah, for instance, which essentially tells you if you consider the models of certain first order theories, what kind of structure does that reveal in this large hierarchy of sets? Some analogous exploration, potentially in terms of this system, should be doable along the h-axis. But that's, as I said, this is a concluding slide, very big picture. And there's some other thoughts that regarding just general data, encodable not as sets, but as homotopy types. But I'm just going to conclude by saying that for me, the soundness and completeness result is kind of intrinsically interesting and meaningful. But one can also think of first order logic with isomorphism as a tool for asking questions. Say in the beginning by analogy to first order logic with equality, later for their own sake. And most of what I spoke to you today is available as this preprint, and it will almost certainly be revised fairly soon and expanded with some new material. Okay, thank you.
All right, thank you very much. I'll now unmute everyone so that we can applaud, and then we'll move to questions. So there we go. And we're gonna mute.
Sorry,
sorry, you're muted. If you want to say something, you need to, or I'll unmute you.
No, I'm okay.
Well, but now we're moving to the Q&A session, so there's probably lots of questions. So don't be shy. Just ask questions.
Yeah, hello. I'm usually very shy, but can I ask a question anyway? Actually, it's a comment. It's a very nice talk. I'm really thank you very much. About you in the beginning, the motivation. Can you get the slide up? You're looking. You say you're looking for a basic theory for HoTT. It's tricky. You can just continue.
You mean that at the very beginning, right?
Yeah.
Say something around here.
Yeah, here. So I always liked one thing about type theory is I liked that you don't need first order logic, that you have this proposition as types explanation, and so hence I thought you don't really need the basic logic because you can define logic within the theory. Now here you seem to be saying, oh no, you're wrong, you do need it. Well, why?
Well, I wouldn't say that you need it. Depends on what you want to do. Wait, I'm getting an echo, Chris. I don't know if this is.
Thorsten, you need to mute your microphone when you're not speaking. Sorry.
Okay. I wouldn't say that you need it, right? I wouldn't say that. I think it's a notion that makes sense and provides a setup which gives you interesting questions to ask. Let me answer by analogy in case that kind of answers your question, the motivational question. You don't really need first order logic with equality either, considered in isolation from ZFC. If you just want a foundation for mathematics, you can just take ZFC to be what we understand as first order logic with equality within it and the axioms of ZFC, and just work with that system and never separate the first order logic with equality within ZFC, right? And you can certainly do that with HoTT and never bother about fragments of it and just take the whole thing. For me, the interesting thing is that simpler systems have more models somehow. So you can study the kind of the large scale structure of models. So let me give you an example of a question that having such a thing as FOLiso allows you to ask. What are the theories in the Univalent Foundations whose type of models is contractible? So homotopy categorical theories. Now, this question becomes interesting and difficult if you have a notion of a theory that is sufficiently general that gives counterexamples and also examples. So that for me is kind of the motivation. So,
thank you. I mean, just to say the obvious, I mean, in ZFC, you always need to introduce first order logic, right? Even if you don't separate it. Whereas in type theory, you sort of get it for free. So in a way, I was thinking when you have these sorts, yeah, and you do lots of things already with the sorts. I mean, like expressing something as inhabited. Yeah, I mean this existential encoding. So in a way, you could almost say, oh, we should put a bit more structure into the sorts. Yeah, maybe like, I mean, you could formulate what are pi types and what are sigma types sort of in your framework, and then all of a sudden you don't need the logic anymore because you can do everything with the sorts, right? Yeah. So I mean, what I do understand and which I also find interesting is that you work in a way in a fragment of HoTT, and you can say, for me, this first order logic with equality is a fragment of HoTT, and in a way, the way you define it, this embedding, sort of shows that's in a way what you're doing, also the way you're thinking. And then you say, there are interesting aspects, the way I can use this fragment, which is useful instead of the whole theory, right? Yeah. That for me, I mean, it would be my interpretation. I have a comment of this completeness theorem. Would it not be possible to model HoTT in this first order logic and get completeness via this?
So you mean something like a bi-interpretability result?
Yeah.
Yeah, that is essentially what the completeness theorem is. Exactly. But the thing that you don't have in FOLiso is univalence, right? So you need to somehow show that every detour you take through univalence is kind of inessential, and that's where the difficulty of the proof is. Yeah, it is. You can think of it the way I set it up. It's a bi-interpretation result. Exactly. Yeah.
But doesn't it mean that we can also that we can interpret HoTT in itself without univalence? I mean,
I think this right. I think yes. I don't quite know what you mean by this. You mean interpret MLTT, say, plus univalence into MLTT?
Without univalence. Yeah.
Yeah, right. I think Michael Ratian has a paper where he first kind of described how to do this. Yeah.
Okay.
Hi. I was wondering if you could say a little bit more about the inessentiality of univalence and sort of how that makes sense within HoTT. Why is this something? It sounds like that to me, not knowing a whole lot about this, that would imply that univalence is either like derivable from other things in HoTT, or like, what does that say about univalence within the theory?
No, it doesn't. I mean, it doesn't. It sounds unfair to univalence because it sounds like it's saying that it's inessential. I mean, somehow it's the complete opposite. That's true. It's extremely essential. What it's saying is that if you restrict yourself to a certain class of theories about which you can express a certain class of properties, if something is true of all those classes of theories, then that true statement can be proven, but without using univalence. So let me give you an example. So consider the fact that under a certain axiomatization, consider the first order theory of groups, like the theory of groups. Okay, even if you ignore the logical aspect of it, right? Consider groups. So in every model, in all models of groups, all groups, it will be true that the identity element is unique, right? Okay, so that's a statement that is valid in the theory of groups. It's satisfied by all models, right? Now, to prove this, that in every group, the identity element is always unique. If you're working in set theory, you might come up with a proof that somehow uses the extensionality axiom of set theory, right? The axiom that says that two sets are equal if and only if they have the same elements, right? But this is never essential. Your use of the extensionality axiom will never be essential because validity, truth in all models, actually coincides with provability in first order logic due to Gödel's completeness theorem, right? So what the completeness theorem that I presented says is something entirely analogous to this. Like if you're ever proving a property as general as, say, in every univalent category, the type of object is a groupoid, then that proof will never use univalence essentially. So, does that help?
Yes, first of all, thank you. That makes a lot of sense in the sense that it's sort of saying this about a restricted class of properties. But just to follow up on that, you said at the very end that the metamath of HoTT is then equivalent via this interpretation to the math of inverse categories. And that sounds like a stronger statement than what you're saying here.
Yeah, that was in the concluding slide, the isomorphism that I put there was more more literary than mathematical. I just meant to say that so when you want to do meta mathematics in the framework of the Univalent Foundation, so my immediate answer is no, don't take that literally. It's false literally. It's kind of a meaningless statement if taken literally. What I was suggesting by this is that if you want to study meta mathematics in the framework of the Univalent Foundations, so you want some mathematical theory that tells you how things are formalized in the Univalent Foundations, right? That's what I understand by the term meta mathematics. Then I think you will be dealing with things like inverse categories almost. They will be implicit in everything you do because inverse categories are the shapes of the contexts that you use in type theory. And whenever you formalize anything in type theory, you formalize it in terms of these dependent contexts. And these dependent contexts can be encoded as inverse categories. And these inverse categories have very nice and elegant mathematics that are kind of totally independent from the type theoretic syntax. So I was just hinting at, for me, this is kind of a nice and fruitful analogy to keep in mind that kind of motivated me in kind of pursuing this. So this, in some sense, goes back to Thorsten's question too. You know, one good thing about FOLiso is it's a fragment of HoTT that has a clean mathematical theory of its own. You know, you can talk about finite set-valued functors and collages and Yoneda and partial Yoneda and all that kind of stuff. You know, in the world of math, they mean things about contexts, but it's also things that we have some kind of intuition about mathematically. So that's another thing that I find nice about it. and I was trying to suggest by this pseudo-isomorphism.
Thank you.
So I have a sort of a reference request, which
Sure.
is that this work seems to proceed from sort of a neat coincidence between the use of inverse categories in folds, and then the fact that inverse categories also have this sort of lovely homotopy theoretic structure that relates to Reedy stuff, and you cited a number of works on that. Now, my suspicion is that there's some earlier work that, because you cited sort of the hot work that deals with inverse stuff and Reedy stuff. There must be some earlier work that explores sort of the nice sort of topological uses of inverse categories, prior to their use in hot, that maybe would sort of be more expository and help to see why it's possible that it can play out in these two different settings in such a lovely way. So I was wondering if you could point me to, or someone else could point to something earlier to start looking at sort of inverse categories in their generality and their topological properties, rather than immediately diving into the world of hot models, which is rather complicated.
Okay, I don't think I have an answer, but I'll say a few things, and maybe someone in the audience might actually know better. Firstly, let me say I agree. I mean, these inverse categories are kind of these wonderful structures. For me, there's something kind of magical about them. They're kind of at the right level of complexity to deal with very many of the phenomena that one is interested in when you're studying dependent type theory and its interpretation to homotopy theory. So I agree with the sentiment. As far as I know, the homotopy applications of inverse categories began with Reedy, or at least in the form in which they have been adapted in the kind of in the HoTT community. I saw a half nod from Chris, so maybe. So you correct me after I finish this. And I'm fairly certain that Reedy knew nothing about Makkai's work on folds, which is the first, as far as I know, adaptation of inverse categories in their logical aspect as signatures. So curiously, they've kind of developed independently, I think. That's what I know of the history. So I think the references would be just the paper that I have here. Can you see my pointer now? Yeah, right? The Makkai paper and things that came out of it. And I guess maybe Schulman's paper, which gives an introduction and references for things in the homotopy direction. I guess that's what I would say. Someone correct me if I'm wrong about the history.
So maybe just to add rather than correct. So Mike's paper that you have there, Univalence for inverse diagrams and complex limits and homotopy canonicity. So Mike gives several very good references there, and I think Andrei Radulescu-Banu's thesis from MIT does a lot of things related to that. So related to Reedy fibrant diagrams on inverse categories with values in vibration categories, and that's the framework that Mike kind of adapts for HoTT in his paper. And then Karol Szumiło actually found great use of it, and his thesis from the University of Bonn is really nice to read, and that's 2014, so it didn't make to the references in Mike's paper. But either Mike's paper or Karol's thesis are very good resources on that. That's what I would add.
Could you type those names of the things that aren't Mike's paper into the chat, Chris? Thanks.
I will try my best, yes. Yes. But before I do that, I'll ask, are there any other questions? We have 5 minutes for more questions.
Yeah, I have a most important question. Is exactly how did you make these slides?
Yes, thank you.
I was expecting this question. So this is the first time I did this. I used the Apple Pen, and which I had been thinking about using to do things like that for a very long time and hesitating, but I think it was very worthwhile. Firstly,
I have an Apple Pen, and then you just run Keynote on your iPad.
Yeah, the Blackboard environment on your iPad, exactly.
Ah, cool. Okay, I have to try this.
It's actually much easier than to tech it. Yeah.
All right. I think we have a question from Dan Grayson, or is it the Apple Pencil? Okay, sorry.
Pencil. Yeah, pencil.
There we go. That was. Thanks for this clarification. All right, we still have 3.5 minutes. I see actually now that you still have like lots of slides past the end slide. So yeah, in the remaining time, would you mind saying like just a tiny bit, a 2-minute bit, so that we still have 1 minute left for my jokes at the end, about the remaining slides?
Okay. Wow. Okay. You spotted them, huh? Yeah. I had the things that I hesitated about putting there. So let me just put it there. I'm not going to have time to explain it, but for me, part of the mathematical interest in developing this framework, especially proving the completeness theorem, that it gives to me a potential approach for homotopy canonicity, and this is something that I've been thinking about for a long time. And the fact, obviously, that you have to prove that univalence is inessential for certain derivations should give you a feel of how it would be relevant. But I see it as a potential avenue for proving homotopy canonicity, and this is something that I'm actively exploring. But it's at the level of speculation, as I say in the slide. Roughly, what I would say to summarize it is that if one could have a axiomatization in first-order logic with isomorphism of a univalent universe with the natural numbers that is complete in some appropriate sense, that is a complete axiomatization, so it doesn't just include a letter U, but describes it in a way that pins it down, then homotopy canonicity would follow from that. So let me leave it at that. Hopefully that's all I'll say about that.
Okay, so this sentence ended at the. I don't remember much from my English grammar lessons, but apparently that was, I don't know, maybe not the best thing to do, but okay. Okay, so let's thank our speaker again. I'll unmute everyone and let's go. Okay, and so, okay, I actually don't have any jokes, unfortunately. So I apologize for that. But the slides were beautiful. The talk was great. And we'll meet again in 2 weeks for Favania's talk on RedPro. And meanwhile, I hope everyone enjoys Brett Kavanaugh's hearings. All right, that's it. Have a great day or night.